Okay. Hi, everyone. Check, check. 1, 2, 3. Can you hear me, guys? All right. Yep. Nikolai, thank you very much. Yeah, I just expect that all of you can get on there and join us in our discussion because I genuinely hope that you will take active part in our seminar right now. So I'll give you a couple minutes to get in there. All right, we have kind of huge audience and only Igor and me are on there right now. So I remind you that you can keep your camera off. It's okay. Yeah, but I expect you to participate verbally at least. All right? Can we consider homework? Yeah, that's the point. Because right now we're going to discuss the homework. We're going to digest all the problems. And I'm going to show you correct answers. And I hope that some of you can present their solutions because, as a matter of fact, students performed very well. They did very well on the first homework. And if you cannot see results right now, I think Zina will make them visible just after our seminars. Okay, but anyway, by the end of this seminar, you will know all the correct answers and all the solutions discussed in details and a little extra knowledge you will also obtain today. All right, so everything you will be in your disposal for the test at the end of the seminar. All right. Okay. So in chat, you can see the link to the collab template. It's empty right now. It contains only settings for all the problems from homework. And I'm going to use it to rebuild the solutions. I hope all the students can participate in this activity and first of all show their own solutions and describe the logic behind their solutions, and then we will discuss it and reproduce the more suitable solution here. All right, so we have 2 classes for this, well, class and a half. All right, first the entire first class and 50% of the next one, because the last part of the following class is going to be devoted for the test. All right. Okay. So let's start with the first problem here. It states that loss x has exponential distribution with an average of 100 million rubles, and we are interested in calculation 95% value at risk. So I would like, I would be happy if someone of you show personal result and the solution. All right, so I'm going to stop demonstration of the screen right now, and I hope someone to share screen as well, okay?
For this task, I have a solution. I hope that it's correct.
Okay, let's see.
And how to show a screen here? I forgot.
I think you should be able to do this
Yes,
because,
I see it.
all right, good.
Can you see my screen?
Yeah, absolutely.
Okay, so
Nice dark theme, by the way.
thanks. I'm gonna explain what I've done. So I've imported some necessary and sometimes extra necessary libraries,
Okay.
and after that I um, generated an exponential distribution with a given mean.
Mm-hmm.
Mm, so if we look up at the syntaxes of this command or just the syntaxes of exponential distribution itself,
Mm-hmm.
we'll find that it r- requires one attribute, and this attribute is 1 divided by lambda, and
Exactly.
it's the math expectation, so it's the mean.
Right.
So, and uh, just I had to make a pretty large sample just
Mm-hmm.
uh, to use the theorem of I don't know of big numbers or something like that. So to discard
Yeah.
the randomness of the process.
Mm-hmm.
So I took 1 million observations and I just put this parameter 100.
Mm-hmm. Yeah.
And oh, well, I guess it could be done easier. I just switched 3 formats, but still,
Mm-hmm.
but still, I draw a histogram
Uh-huh. Nice.
and I put a confidence level, and after that, I just created a var as we
Uh-huh.
discussed in our class,
Uh-huh.
and used the interpolation lower.
Mm-hmm.
So, and the result is approximately 300. If I
Yeah.
relaunch it, it will be not the same, but around.
Yeah. Yeah, absolutely. Okay. So you decided to go the way with the Monte Carlo simulation, right? So
Mm,
you generated the sample, the pretty large sample, and apply empirical estimation, right?
Why
yes.
interpolation is lower?
Here's a good question. Can you answer it?
Yeah. So, uh, because, uh, okay. Uh, as I remembered from our seminar, we did lower when we position.
Yeah. Yeah. So the logic is following. So if you should consider your distribution as a P&L distribution, and the main question you should answer before estimating value at risk is where the losses lie in a right tail or in a left tail. So what we know from the problem verbally. We know that the losses are described with exponential distribution, and we definitely know that exponential distribution is defined on the positive axis, right? So it's defined for all outcomes non-negative outcomes, right? Exactly. So that means that the entire distribution describes only losses. There are no profits, right? So that means the greater number, the greater outcome we see, that means the greater loss we experience, right? And that means that we should deal with the right tail, okay? Just like we did when we tried to assess risk of short position, right? When we uh, face the losses, when we will face the losses when prices go up, right? So when in a regular long position you experience profits, right?
I have a little bit misunderstand how
Okay.
it can be possible that when I buy some stock, I want it to be with a high price and
No. Here is the deal. Look, when you buy price, that when you buy stock, that means that you take long position.
mhm,
All right?
yes.
That's how terminology works. The long position means you buy something. Uh, or you take position that allows you to gain when some risk parameter or risk factor goes up. All right. So if you think of returns as a risk factors, so taking long position, you win when returns are um, positive, right? So this is the standard position when you just buy. But you can go short. That means that you borrow stock from someone. You don't own it, you just borrow it and you sell it on the market. And you have the option to buy it back at lower price. And in this case, you will benefit from dropping prices, right?
Mhm.
So you sell something on higher, then you buy it back. The same case works when you go short on stock using different instruments like futures or forwards. So, for example, when you sell futures or you sell forward, right?
Mhm.
So you benefit from falling prices. And
Okay.
and that just means, yeah, and what it means that you take different actions to take different exposure to the risk factors. Remember from the lectures when we were talking about risk factors and exposures. So risk factors is something that you don't control. So you don't control your prices, right? But you can take right or desirable exposure to those factors. So, for example, you can go short and you can go long, and that will transform the outcomes of your own profits and losses regarding dynamic of the risk factor, right? Is that clear?
Yes.
All
Mhm.
right, great. So Maria has another question. When we short position. Okay, Maria, we win on short position when prices fall. So when prices go down and we observe negative returns, we gain if we short on stock. All right. So this is kind of take opposite position to buying, right? So should we make an assumption about the size of the sample? I thought if we did not have it, so there are not enough data. As a matter of fact, in this particular problem, going Monte Carlo is a little excessive. So actually, you can uh, determine and you can find evaluate risk going analytically. So actually, you can perform parametric estimation here, and we will do it right now. But at the same time, the greater sample that you generate from your distribution, if you decided to go Monte Carlo, um, the greater precision you will ensure for your estimation. At least what we can see in this particular problem, that for suggested answers, so actually suggested answers are very well dispersed. So 300 is a much greater than 200 something, right? So you definitely understand that uh, you won't need to go billions, quadrillions, or something like that to ensure pretty narrow tolerance for estimation, right? So actually, I think even performing something like 1,000 or 10,000 will be pretty enough to come up with the right conclusion about the var magnitude, all right?
Yeah, but if we take some kind of small sample, for example, 10, so we
Yeah,
have
yeah, absolutely.
another result.
Yeah, yeah, absolutely. Yeah, but it's not that you're gonna get another result because actually you will need to resample, uh, make resampling a lot of times and actually get the distribution of your estimation. And this estimate and this distribution will be very well dispersed, so dispersed that you cannot come up with uh, pretty clear decision about pretty conclusion about the magnitude of the value at risk, the quantile, right? But if you run simulation with a great number of scenarios and outcomes and observations, you can actually be sure that even if you run only single simulation, it will be very close to the real value of the statistic, right? So, okay. Um, Nikolai, great job.
Thanks.
Yeah, and the answer is correct. The only thing that I would like to add is just to rebuild um, the direct estimation with the parametric means, if you don't mind. So let me uh, get the sharing facility for myself. So please stop sharing, and I'll
Mhm.
do. Um, okay, and I'm going to. Okay, great. So here's another one. Okay. So here's the deal. I have prepared self a code, and I will um, go a little deeper into details of logic, how we actually solve this problem. So, as Nikolai absolutely correctly said, um, we need the distribution, we need the exponential distribution, and first of all, we need to set parameters of this distribution correctly, all right? So, what we do for this? First of all, let me import necessary libraries. And first of all, I'm going to fix my distribution. I do this with stats module from SciPy. As most of you probably remember, this module contains a lot of um, implemented continuous and discrete distributions. So I'm going to go with exponential one. Here is an object expon for this. Okay. And the basic idea of this distribution is that the standardized exponential distribution that that generates by default from the stats is exponential distribution with the parameter 1. So probably you remember the lambda equals 1. And as you remember, the mean of this distribution equals 1 divided by lambda. So lambda actually is something like frequency of occurrence some event, and the in this in this case you may think about mean as of the distribution as the mean number of events. All right, so by the default, this distribution has some mean, which is clearly 1 if lambda equals 1 for standardized exponential distribution. And And that's it. So any other standard statistics are um, not really critical in this situation. What we actually know, we know that to get customized distribution, we just need to rescale it. And to rescale it, we use parameter scale that corresponds to the magnitude of the mean. All right. So what we can do here, we can set this distribution. So we can see here parameters. And the parameters that we actually need, 0 and our mean. And mean from our problem is 100. So I actually put mean here. And let's see if everything works. Great. What I can do here, actually, I can plot the distribution and see how it looks like. So let me do it this way. I'm going to get some linear space that is just a series of numbers. Let me put something like this. And then I'm going to plot this distribution.
Excuse me.
Yeah.
Will you send the following code later, or should we print it parallelly?
Actually, this code will be available through the link that I provided.
Okay.
So if you would like, you can follow me and write your own code. But by the end of the seminar, everything that I write here will be available to you. All right. So if you just want to watch, okay, it's totally fine. All right. Okay. So let me do further. So I have my own distribution, and I just take density function, apply it to my line space, my vector, and I just play around with a little style. Let me draw all the lines with red dashed lines and let's see what's going to happen. Okay, so here is a distribution, and now I understand that the scale of the distribution is something very large. So I definitely understand that the right answer should be somewhere here around, right? But let's find it out exactly what it is. I'm going to apply the method PPT. Do you remember this method? So this is a percent point function which deals with the quantile measures, right? So I have my own distribution. It is already parameterized. And everything that I need is to apply PPT method. And here I need to put right number in it, right? So here we remember that we deal with the distribution representing losses. So the greater the number of x, the greater the loss. And I understand that I should find value at risk not on the left side of this distribution, not here, not somewhere around 0, but somewhere in the great numbers, right here on the right tail. So I understand if level of the value at risk I'm searching for is 95%, I should put the parameter of 0.95 right here. So just to cut 5% of the probability on the right-hand side, right? So now let's see what we're going to see. Are 5% equals, and let's see. Oops. Invalid syntax.
You have PPF, not PPT.
No. I missed comma. I just missed comma. So this is the text, and this is the value should be printed out from the variable. So I just missed. Okay, so here it is. Okay, this is something that is very close to 300. And so you may guess now that we put 300 in our answers just to make sure you're not going, so make sure, so that we make sure that we work with just nice numbers without all this digits on the right from the point. All right, so we kind of round it up. Okay. So this is it. It's pretty easy, right? So now you understand if you can actually parameterize your distribution, you can just apply all the parametric methods from the stats and be happy. But everything that Nikolai did, everything is absolutely correct. So, and provides the same answer. Okay. Okay, can we move on?
Yes, thank you.
Great. Now let's move to the second one, to the second problem. And this problem is a little more tricky. So what we know is that asset returns are normally distributed. And we know some constraints, and we're aware of some constraints on expected return. So we know that expected return is non-negative, so we're not expecting losses. Typically, we expect to gain something, or at least not to lose anything. All right. And we also aware about the value of value at risk on 95% of confidence level, right? So the problem is to identify which of the following numbers can be, so it's just the plausible numbers for expected shortfall matrix, having all other information from the problem. Okay. So any volunteers to show their results and the logic? Come on, guys.
I only have an idea. I don't have the solution.
Okay, let's start with idea.
So mm, the problem was to build a distribution with a given var. So I didn't really find any ways to do it, but maybe we can use the formulas from the first task, which you just showed us, and
Okay.
use them as a conclusion to var through the PPF function. No, but I don't know how.
Well, actually, that's a nice idea. So what we actually know, we know that the normal distribution is pretty nice distribution. So probably we should start with something simpler than we actually face in this problem. So let's start with the standard normal distribution for a second, just for a second. Probably you all understand that value at risk for the returns described with the standard distribution, it's just a quantile on the 5% level, right? Because we're talking about returns, so losses on the left-hand side, right? So in the left tail. So not, for example, 95% value at risk is just a quantile at 5% level, right? So it cuts 5% on the left. Okay, And at the same time, not 1.96, but 1.65, because we talk about one side critical value, not two sides, right? Because 1.96 it is a quantile of 2.5%. Okay, but I like the way you think. Okay. At the same time, we can calculate expected shortfall for a standardized distribution as well. Okay, and a little spoiler alert, it's going to be pretty close to 2. So we can calculate expected shortfall in var at the given confidence level for a standardized distribution. But now let's think about what's going to change if we consider general normal distribution. What's going to happen with estimates for the standardized distribution? It's very clear and very easy. So probably you intuitively understand that changing sigma, right? So the changing variance of the distribution will rescale var and expected shortfall by the same, by the same multiplier, right? So for example, we still have centralized distribution, so centered at 0, so with no mean, right? So the mean is 0. So we just change sigma. So new var is going to be the var for standardized distribution just multiplied by this sigma. And the same applies for the expected shortfall as well, right? So you just rescale normal distribution, nothing else. Great. Now what's going to happen if we apply non-zero mean? And we know that this is possible. And we know that our value at risk in the left tail. So everything actually, mean shifts the distribution, right? And if mean is positive, right? So what's going to happen? Our value at risk measure will fall, right? Because we shift our distribution into positive outcomes, right? So the extreme losses are less likely right now, okay? Do you agree? So if we shift...
Maybe you can draw the graphic of such distribution.
Okay, no problem. Let's do this. Okay. First of all, let me start with this. Before I write any code, let me write some formulas just to make sure that you understand the logic. Okay. Let me. Okay. Hold on a second. The text one. Okay, I'm going to write some code on the left, and you can see the result on the right. So just follow this region of the screen, okay? Okay, let's consider.
Do you demonstrate your screen?
Oh, sorry,
We can't
I'm
see
not.
it.
I'm not demonstrating screen. I'm sorry, terribly sorry. Thank you for reminding me. Yeah, thanks. So what I'm gonna do right now, I'm going to just to write some formulas. So you following this region of the screen, right? On the right, because formulas are going to appear right here. So I start with the normal, standard normal distribution. Okay, this is the standard normal distribution. For example, we consider some random variable epsilon. So what I actually would like to do, I'm trying to find var on 95% confidence level. That's what I'm concerned about. And let's solve the problem for expected shortfall and for the var for standard normal distribution. It's pretty easy. So what we actually understand, we understand that var in the settings, var is just a quantile of standard normal distribution. Phi minus 5%. And then this. Okay. All right. I think it should be pretty clear. It's not a rocket science. And as for expected shortfall, it's just, let me use the notation small e, standing for expected shortfall, just a standardized. And I applied the 5% as well. That's just,
Why is it 96?
no, I'm working with the left tail, so I'm going to
No, why
keep this.
expected shortfall is 96%?
It's just a
Ah,
typo. Sorry,
okay.
thank you. Yeah, thanks. And okay, so I'm gonna go with minus infinity to the q quantile here. Okay. And here I have x multiplied by density function of standard normal distribution, right? Okay. So, and remember that we follow the convention that value at risk and expected shortfalls, they are positive numbers, and quantiles and expectation in a tail here are definitely negative, so I put minus here. Just to make sure that everything is fine. Okay. Good. Now, if I consider general normal distribution, represented by this linear transformation, okay, and this distribution now is some normal distribution with parameters mu and sigma. So what I know for this distribution, I know that value at risk can be expressed as the linear transformation of value at risk and expected shortfall of standardized normal distribution, right? So here I can easily write it is just minus, now let me start with this. Let me write it down like this. It's going to be rescaling of the standardized var. So it's going to be minus, so it's going to be sigma minus Q95%, right? So sigma just multiplied by the quantile. And I also understand that I have to deduct mu value from this. So now let's see in the code. Let's see standardized distribution, which is going to be normal and general distribution. I'm going to apply some positive mean, let it be 1%, and I'm going to apply some sigma, let it be let's say 5%. Okay, so I have these two distributions. Let me briefly copy this code from above, and I'm going to show these two distributions. I just change a little
Excuse me.
the limits of the lin space. Yeah.
What are the default parameters for norm?
0 mean and 1 location 0, scale 1.
Okay.
Okay. We will see right now when I plot all the lines. So I start with blue lines for standardized distribution. Don't forget to put right here correct references to the standardized and generalized distribution. Here I put my label standard, and here I put the label general. Okay, general. Okay, and I also show legend. It's gonna be enough. All right. All right. Let's play with, let's take another parameters just for the demonstration purposes, just to make sure that picture is quite more representative. All right. So the blue line is a standard distribution, right? So what's happened when I use another sigma? So I apply different volatility. I just make it more narrow, right? So I kind of push it from the two sides, all right? So I compress it, right? And when I add some positive mean, I just shifted this distribution. So what we can clearly see here, if the distribution was standardized and we have our value at risk somewhere here, right? Somewhere here. For the new general distribution shifted and rescaled, first of all, we go into, let me do this. Let me, first of all, rescale it, and then I shift it for, for illustrative purposes. So when I apply another scale, which is here less than 1, I see the compressed distribution, and now I definitely understand that my value at risk goes somewhere here to the right, to the center, right? So actually, it makes my value at risk less, okay, in magnitude, yeah, because it's just rescaled. And now let me add some positive values. So like we have positive expectations about returns. So on general, on average, typically in a series of investments, we used to uh, actually gain on this investment. All right. And what's going to happen? We see the shift. So this shift makes my value at risk even less, right? Because the quantile shifts to the right. And that's what we see here in the formula, right? Look, here is my value at risk for standardized distribution. I rescale it by sigma, and then I subtract mean, right? And the same formula actually applies to expected shortfall. So nothing's going to change here. Oops. If I write the same equation um, for expected shortfall, right? So what we actually now can see from here, that everything that defines value at risk and expected shortfall is just expected shortfall and VAR for standardized distribution, and we can easily calculate it right now, right? We also know that linear transformation of standard normal distribution changes VAR and expected shortfall in the same manner. And what we actually know from our problem, we know the VAR, the value of VAR, and we know some constraints on sigma and mu, right? So we know that mu is non-negative by the problem settings, and sigma is non-negative by definition, right? So now we can actually express mu and sigma from these two equations. It's very easy to do. So sigma is going to be um, expected shortfall minus value at risk divided by the same difference by for the standard distribution, right? So it's going to be E minus Q modified. Slash here. Okay. And it's very easy to see that mu from this equation is going to be just, for example, here. So sigma times, for example, minus Q 95% minus value at risk. That's it. This parenthesis here. All right. Okay. And now it's pretty easy to understand. Now we calculate Q 95% and E 95% for standardized distribution, right? var, we know var, so we can put the value for it in all those expressions. And everything is needed here is to put all the options for expected shortfall and calculate sigma and mu and check if those values are non-negative. If these two constraints are not hold, do not hold, so that means that expected shortfall value from the options is invalid. All right. Okay, so now let's see the values for standard distributions. Standard distributions, very easy to see. Q 95% equals standard distribution F oh I beg your pardon, I just put wrong numbers for Q and E everywhere. Sorry about that. It's just quantiles for in the left tail. So let me correct myself just to make sure that you have correct formulas here. All right. So I put. So let's recall the level. It's 0.95, and I put 1 minus level here. Okay, and I'm going to find E95% for okay, I have integrate here. No, I need to identify them separately, I guess. Okay. Because here's a little trick with integration, because actually it's two valued output, so I need to play around with it a little bit. So I have int, and I have quad for integration. I put lambda here as x multiplied standard distribution x. Okay. And I put minus inf. Just oh no, it's from numpy inf. Sorry about that. And Q here. So I think everything is correct right now. So, no, I missed that. Okay, I think everything is down here. So now I need to put minus Q and minus E here just to find out what those values are. Nope. I think I missed something here. Oh, first of all, I forgot to put level here by definition. And okay, it's should be EF. Sorry about that. So now everything is correct. Okay, so now I can see that value at risk for standardized distribution and expected shortfall for standardized distributions are those that we expected. So it's 1.65, right? So you know this quantile, you're familiar with this. And now you know that expected shortfall for standardized distribution is just 2. So it's pretty close to the quantile of 97.5%. Okay? Good. So now we actually can see and we can do some experiments with mu and sigma, right? So we can write sigma here. And sigma is just it's just E minus Q divided by var minus, oh no, expected shortfall. No. Sorry about this. Expected shortfall minus var divided by expected shortfall minus var for a standardized distribution. And what we're going to do, we go into specify var and expected shortfall for general distribution. Well, var is known, it's just 100, right? Yep. And we should check these values for expected shortfall. Okay. I also going to write the same expression for you. Here is my multiplier. I'm going to multiply it by minus Q. And I'm going to divide it. And I'm going to subtract var. Okay. So here we are. Okay. Now let's take a look at these values. I'm more than sure that you can eliminate one of those values without any calculations. Which one?
75.
75. Why?
Because expected shortfall should be, in our case, greater than value at risk.
Well, at least it's never less than
Yes.
var by definition, right? And that's the case that we can see right now. So we eliminate this option completely and never turn back to this. So all other options are more reliable, right? Because at least those values greater than 100, that is var in our settings. Okay, so everything that we need to do right now is just to put those values into these formulas and see what's going to happen. So let's check first value 105 and see what's going to happen. So first of all, we see that um, I missed some minus somewhere. I think I missed minus somewhere.
In front of Q and E? No. In no,
Here.
the row 13 and 14. In formulas, we use minuses.
Oh, yeah, correct. So I should do this, right?
Yeah.
Yeah.
You
Yeah,
can do
thank you.
so.
Yeah, thank you. So this is kind of tricky thing. Okay. All right. So, okay, we see positive sigma, but at the same time, we see negative mu, right? So the negative average. And what we know from the settings, we know that expected return is non-negative. So actually, we have to eliminate this option. All right. Let's consider another one. 135. Well, good. Now we see um, positive mu. No. I think I missed something. I think I missed something. Because, yeah, this is a 2. So I have here should be greater plus. There's a minus q. So this is yeah, so this is the negative value. This is the positive value, and that's correct. And so we put it right here, and I put it here. So this is 1, and the value at risk. So this is a positive value, and this is a negative value. Um,
Shouldn't it be the Q in mu? Well,
here.
21st. Yeah. Shouldn't it come with plus? Because we determined it with minus, but our Q is determined with plus without minus in our code. No?
Uh, let me think about yeah. So this if it's a positive value, so it's rescaled, and I deduct mu, right? And this is a negative value. Yeah, I think you're right. Yeah. So actually, that means, yeah, absolutely. So that means actually
What
that's
is the package synced? In the first row, you import syn, and on the 14 line, there is a synced. Is that one package?
I'm not sure that uh, I catch the idea of your question.
I got error, name synced is not defined.
It's supposed to be defined because this is the 4th line in first cell. So I'm importing integrate submodule from SciPy and
Okay.
name it as sint. Okay, so
Yes.
that's what you can see in the preliminary. Okay, so yeah, so actually, yeah, correct or not. Something something happened here. Um, okay, so this is a quantile. We rescale it, and if it's positive, now we state it as a positive. We divide, yeah, we subtract the mu. Okay, this is correct. So now I can do.
Sorry, can you please explain again why expected shortfall can't be less than or?
Because expected shortfall by definition is an expectation of values greater than var. This
Well,
is
but
by definition, because expected shortfall works with the region of the distribution that contains extreme losses, and those extreme losses are greater in value than value at risk. Value at risk is something that sets boundary for typical losses. All right, so the losses that you cannot suffer with a certain degree of probability or confidence or a confidence level. Okay, and when you deal with expected shortfall, you actually try to calculate conditional expectation in the region where losses are greater. Okay. Um, let me rewrite this formula just to make sure that I do everything right. Because, okay, so for example, taking this first equation from the another one. Okay, yeah, that's what I got. And then I put sigma back here, and this is the positive one, and I'm subtracting positive now. So if the Q is negative here, yeah, it's supposed to be negative here. So the entire is positive, and now I'm trying to deduct positive. So this is not right. Kind of confused. Um, and this is valid. That's valid as well. Nonsense. Which is nonsense. Probably I missed some sign somewhere. So this is the first one, this is the first one, and this is the value. So the value is greater, and then I deduct mu, right? And that's what I do here as well. Okay, and this is the difference between expected shortfall in var and expected shortfall here in var here as well. Okay, everything holds here. So that means
Maybe we should take a break and after that look it
um,
with a fresh eye.
so the greater expected shortfall means the greater sigma. Okay, and why var here? Um, yeah, I'm missing something. Okay, let's have a break. I think now time for a break, right? Okay, and after the break, I'll clarify everything here and share the results with you. All right?
And we
Okay, we
start
have
at 13.
30 minutes for the break. If you have some questions, please come back 10 minutes earlier. And just before the seminar, the next classes starts, yeah, I can answer your questions. Okay? But now let's have a break.
So we continue at 1 p.m., right?